In Chapter 3, we're going to study polynomial and rational functions. In Section 3.1, we begin by discussing quadratic functions. A quadratic function is a function of the form f of x equals ax squared plus bx plus c. The graphs of quadratic functions represent almost kind of like a U-shaped figure that could look either like a right side up U or a upside down U, and the proper name for that shape is what's referred to as a parabola. For functions of this type, the parabolas come in two different shapes, like we said, the ones that open upward and the ones that open downward. They can be classified based upon the leading coefficient, which is what we call the value a, which is the coefficient of the x squared term. Whenever a is greater than 0, the parabola opens upward, and whenever a is less than 0, then the parabola opens downward. So for positive leading coefficients, we get an upwards parabola. For downwards opening parabolas, we get a negative leading coefficient. One of the most important points, if not the most important point on a parabola, is what's called the vertex or the turning point. When a parabola opens upward, we see that the vertex would produce a minimum for the function, and when the parabola opens downward, the vertex ends up being a maximum. Okay. A parabola is symmetric through the vertical line that passes through the vertex, and that's what we call its axis of symmetry. So let's suppose you have the center, not the center, but suppose you have the vertex that's located at h comma k. If that's the point where the vertex is at, then the vertical line x equals to h is going to be an axis of symmetry for that parabola. A very convenient form for our quadratic function is going to be what's referred to as standard form. A quadratic function in standard form can be written as a times x minus h quantity squared plus k. The vertex will be at the coordinates h comma k, where the h value, properly speaking, is a number that sits behind a subtraction sign inside of this parenthesis behind the x, and then the y coordinate of the vertex k is literally whatever number you see on the outside being added or subtracted. For some students, the way I kind of hear that they like to memorize this is that if you look on the inside, whatever's with the x, it's the opposite sign of whatever you see on the inside. So if you think of this not as subtracting by h, but if you think of it as like a negative h, then a positive h is going to go here, and literally wherever you see on the outside for the vertex, the y thing, is going to be the y value of the vertex. The leading coefficient, if you were to expand this out, we see that it's the number out in front multiplying to the parenthesis that is the leading coefficient. And as before, if a is greater than 0, it opens up, and it's going to open down if a is less than 0. We also have the line of symmetry. It's going to be the vertical line x equals to h, where h is the x coordinate from the vertex. In order to graph a quadratic in standard form, we first want to determine how it's going to open, how it opens up or down. That's dependent upon the sign of a. We then want to identify where the vertex is at. In standard form, the vertex is at h comma k. We would also like to list some special points that might be on the graph, namely any of the intercepts. So x-intercepts or y-intercepts. To find the x-intercepts, you set f of x equal to 0 and solve for x. To find the y-intercepts, we evaluate or compute f of 0. With that given information, if we have the vertex, some additional points from the intercepts, and if we know how the graph opens either up or down, we should be able to put all that information together along with the axis of symmetry to draw a very rich and detailed graph of the quadratic function. Let's take a look at example 1. We are asked to graph f of x equals negative 2 parentheses x minus 3 squared plus 8. In order to graph this, let's first notice that the coefficient for a is negative 2, which is less than 0, so that implies that this thing is going to open down. So it opens down. We also want to give the coordinates of the vertex. Because this is in standard form, we can just look at it visually. If it's a x minus 3 on the inside of the parentheses squared, then it's the number 3, which is the x coordinate of the vertex, and the number on the outside that's being added is 8. So we have a vertex at 3, 8. Let's now go ahead and find our intercepts. For the x-intercepts, we are going to set f of x equal to 0, and then we're going to solve for x. Let's do that. We have negative 2 parentheses x minus 3 squared plus 8 equals to 0. To solve, let's subtract 8 from both sides. Like this. Next step would be to divide by negative 2. Again, after all, what we're doing here is we have a perfect square quantity, so we're going to be able to use the square root principle on this. Negative 8 divided by negative 2 is positive 4. And then the very next step, to get the x by itself, we're going to take the square root of both sides. Keeping in mind that when you take the square root of a number, we have either a positive or negative radical of it. So this gives us plus or minus 2. And now let's come over here and split it apart. We have x minus 3 equals to negative 2. We have x minus 3 equals to positive 2. If we add 3 to both sides, we get x equals to 1. If we add 3 to both sides, we get x equals to 5. So these are the x values for our x-intercepts. Let's write them as ordered pairs. So they're going to be the ordered pairs 1, 0 and 5, 0. Let's find the y-intercept. Recall the y-intercept is just an evaluation. To find the y-intercept, we evaluate f of 0. F of 0 is equal to negative 2, 0 minus 3 squared plus 8. This is going to be equal to negative 2 times 0 minus 3 is negative 3. Negative 3 squared is positive 9 plus 8. That's negative 18 plus 8, which is going to be equal to negative 10. So we get the order pair 0, negative 10. That is our y-intercept. And then the last thing I'm going to do that's going to help us to graph this is let's get the axis of symmetry. Or perhaps the line of symmetry might be a better name. Either's appropriate. It's always x equals the x value of the vertex. So x equals to 3 is going to be a line of symmetry for our parabola. Before I do much else, let's go ahead and draw that line of symmetry. This parabola should be symmetric with respect to this vertical line. Let's now go ahead and plot our points starting with the vertex. The vertex we said was at 3, 8. That's right here. We have x-intercepts of 1, 0 and 5, 0. And we also have a y-intercept of 0, negative 10, which would be right here. And now all we're going to do is we're going to go ahead and connect our dots, keeping in mind that the shape of this should be a parabola, so it's a curved shape. And it's going to open downward forever, because we know that, because a was negative. So make sure you put your arrows here. And then try to keep it nice and symmetric on the other side, like this. So there you have it. This would be the graph of negative 2 parentheses x minus 3 squared plus 8. Let's take a look at example 2. Again, first thing we want to determine is how does this thing open. Notice that here, there's no number in front, so it's understood to be 1. So a is equal to 1, which is greater than 0. That means it's going to open up. We can now determine the vertex. It's going to be negative 3, 1. Remember, it's kind of the opposite of the value you see in the parentheses with the x. If we see a positive 3, x plus 3, then it's -3 is the x value for the vertex, and the number on the outside, that +1, is literally going to be the y coordinate of the vertex. So far, so good. Let's now go ahead and find some points. Let's find our x-intercept. Again, this is done by setting f of x equal to 0 and solving. If we set x plus 3 squared plus 1 equal to 0, we now want to solve this. Again, when you're solving for the intercepts of a quadratic in this kind of form, you can always try to use the square root property. We're going to begin by subtracting 1 from both sides like this. The next step is we want to get the x by itself, so we're going to do the square root of both sides, remembering to do a plus minus on the right-hand side, and we get this. X plus 3 equals plus or minus the square root of -1, which is I. We know this solution is a complex number, but it's not a real number. And whenever we're graphing in the xy plane, everything we're graphing is real values. So the takeaway and the interpretation of this is that this particular graph is not going to have any x-intercepts. And that'll make more sense in a minute. But again, if you get complex numbers, those aren't things that we can plot. So this graph will not cross the x-axis. We will, however, have a y-intercept. To find the y-intercept, we're going to evaluate f of 0. F of 0, if you plug 0 in, will give us 0 plus 3 squared plus 1, which should be equal to 10. That's 9 plus 1, which gives us 10. So the y-intercept has coordinates 0, 10. And last but not least, we can do our axis of symmetry, our line of symmetry. The vertex was -3, 1. So the axis line of symmetry is going to be x equals -3. So let's go ahead and begin by plotting that first. We have x equals to -3, which would be this vertical line right here. Next thing we're going to do is plot any points we have. We have 2 in this case. We have -3, 1, which would be right here. And we also have a y-intercept of 0, 10. And the other thing that we know is we know that this graph is going to open up. So to the right of the axis of symmetry, it's going to look like this. Going ahead and doing my arrow. But we don't have any points that lie to the left of the axis of symmetry. That, however, is not really a big issue. Remember, it has to be symmetric. So one of the things, if I kind of pick on here for a moment, this y-intercept, this point is 1, 2, 3 units directly to the right of the axis of symmetry. That means we also have to have a point that's going to be 1, 2, 3 units to the left of that axis of symmetry, which means that we're also going to have the point -6, 10 on the graph. And you can add that additional point through symmetry to help to fill in and create a very accurate graph of this function. So there you have it. This would be the graph of x plus 3 quantity squared plus 1. By looking at the graph, it also makes a lot of sense why we didn't come up with any x-intercepts. Notice that whenever a parabola opens up, the vertex is going to be the lowest point or the minimum on that graph. And then from there, because it opens up, there's going to be no places where this graph will ever cross or come down and intersect the x-axis. The next topic we're going to look at is graphing in the form ax squared plus bx plus c, which is the general form of a quadratic formula. What makes this one a little bit unique is the fact that without it being in that standard form, we can't just visually look at it and tell what the coordinates of the vertex is going to be. We can still at least determine what type it is in terms of whether it's going to open up or down based upon the sign of the coefficient of A, but we're also going to have to be able to find the vertex now. And this leads us to what's called the vertex formula. The vertex formula, so let's suppose we have our quadratic function that's written in the form ax squared plus bx plus c equals to 0. The vertex is going to be located at the following point. This, keep in mind, this is an ordered pair. It's a point in the plane. The x-coordinate of the vertex, this is really the thing you have to put to memory, is it's negative b divided by 2a. So that's going to be the x-coordinate of the vertex. And then comma, to find the y-coordinate of the vertex, you simply take whatever that number is and you evaluate the function at it, and that will give us our y-coordinate. Okay? If it helps, you may have seen this kind of somewhat before. Where is the negative b over 2a coming from? Well, if you recall the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This is something that all of you should have memorized. If you kind of just exclude or throw away the plus or minus the radical part, the negative b over 2a, that's the x value at which the vertex is going to be located. With that additional information, we should now be good to go. We can now find the vertex of this by using the vertex formula, negative b over 2a, and then comma, the function evaluated at negative b over 2a. That will tell us how the parabola opens. So that tells us the vertex of the parabola. We already know how it opens based upon the sign of a. We find the intercepts the same way. You set the function equal to 0 and solve. And then to find the y-intercept, you simply evaluate the function at 0. Let's graph the quadratic function f of x equals negative x squared minus 2x plus 1. And there's a follow-up question where they ask us to use this information to identify the function's domain and range. So let's do that as well. Again, first things first, let's determine how it opens. In this problem, the leading coefficient a is equal to negative 1, which is less than 0. And because it's less than 0, that means that this is going to open down. So this opens down. The next thing we want to find is the vertex. And this is going to be done using the vertex formula. It's going to be negative b over 2a, and then f of negative b over 2a. The coefficient for a is negative 1. The coefficient for b is negative 2. And even though we don't need it for this formula, notice that if you're curious for completion, the value for the coefficient c would be positive 1. So let's figure out the x value first. It's going to be the negative of b divided by 2a. That's the opposite of b divided by twice a. B itself is the number negative 2. A is negative 1. So we're going to get positive 2 divided by negative 2. And positive 2 divided by negative 2 should give us negative 1. So the vertex is going to be located at negative 1, comma. Now to find the y value for the vertex, we simply take that value negative 1, evaluate the function at it. This is the opposite of negative 1 squared minus 2 times negative 1 plus 1. This is equal to, negative 1 squared is positive 1, but then we take the opposite of it, so we get negative 1. Negative 2 times negative 1 is a positive 2 plus 1. And if we add that all up, we get 2. So the vertex of this parabola is going to be located at negative 1, comma 2. We now want to find the x-intercepts. To find the x-intercepts, we set the function equal to 0 and solve. So when is negative x squared minus 2x plus 1 equal to 0? One of the convenient things you can do to solve this equation, notice how the leading coefficient is negative. If that happens, oftentimes it can be convenient to multiply both sides of the equation by -1, just so we can have a positive leading coefficient to work with. That will help us not only if we're trying to factor this thing, but also if we're trying to use the quadratic formula. So we get this, we get x squared plus 2x minus 1 equals 0. And now from here, you could try to factor this. Unfortunately, this one will not factor. So let's try to use the quadratic formula. A is 1, B is 2, and C would be equal to -1. So the solution to this equation are going to be x equals the opposite of b, that's -b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. This is equal to -2 plus or minus the square root of, we have 4, that's 2 squared. Then we have -4 times 1 times -1. That will give us a +4, all divided by 2. This is -2 plus or minus the square root of 8 over 2, which is -2 plus or minus. Now the square root of 8, that will reduce. The square root of 8 is the same thing as the square root of 4 times the square root of 2. And the square root of 4 is 2. So we get 2 squared is 2, like this. And now lastly, there's a common factor of a 2 in the numerator you can factor out. We get -1 plus or minus the square root of 2, all divided by 2. And we can cancel that common factor of 2. So this cancels with this, and we get our 2 x-intercepts. They are x equals -1 plus the square root of 2, and x equals -1 minus the square root of 2. Now, in a situation like this, we always want to give the exact answer like we did here, but since we're ultimately going to have to end up graphing this thing, we would also kind of like to have an approximation so we know about where to put it on the graph. For example, -1 plus the square root of 2 is approximately about 0.4. I'm just going to go to the nearest tenth, because that's probably about as accurate as our eyesight will let us graph these things. And then if we look at the next one, -1 minus the square root of 2, that's going to be located at -2.4. So -2.4. So we do have our x-intercepts. Let me just kind of label them. They are 0.4, 0, and -2.4, 0. So those are x-intercepts. We now want to find the y-intercept. Let's do that. To find the y-intercept, we just evaluate the function at 0. So f of 0 is equal to -0 squared minus 2 times 0 plus 1, which is equal to +1. So our y-intercept is 0, 1. And then the last thing we can discuss and put on here is, again, that axis of symmetry. So axis of symmetry, it's going to be x equals the x-coordinate of the vertex, which we said was -1. Let's put this all together so we can graph this thing. X equals to -1 is right here. Let's now plot any of our points, starting with the vertex. The vertex is located at -1, 2. That's right here. We have x-intercepts of 0.4, 0. It's going to be just a shade less than a half, roughly about here. We also have another one at -2.4. It's going to be roughly about there. And we have a y-intercept at 0, comma 1, which is here. The points are already kind of leading us in the right direction, but we know from before that this thing should open down. So now we can go ahead and complete the graph. And there you have it. There's the graph of negative x squared minus 2x plus 1, which was a parabola that was presented in general form this time. The same techniques we used for the last couple examples are present here again. The only thing that makes this one slightly different is the use of the vertex formula to find the vertex. We're not quite done. I take that back. We also were asked to find the domain and the range. Again, the domain, you're looking on the x-axis, how far to the left, how far to the right does this go? Well, it's a parabola, it's a polynomial, so we know it's going to be all real numbers. This graph goes all the way to the left and all the way to the right. If we're looking for the range of this function, now we're going to look on the y-axis, so we want to know how far down to how far up does it go. On the y-axis, this thing's going to go down and down and down all the way towards negative infinity, and it goes up to the maximum height, which is given by the vertex value, which is at 2. So the range of this function is going to be from negative infinity to 2. One of the things that we can also do is we can classify the minimum and maximum values of the quadratic function based upon the way that it opens. So remember, if a leading coefficient is positive, then that means that the parabola is going to open up, and that will provide a minimum value. Where that minimum value happens at, it occurs at the vertex, and the y value of the vertex will actually give us the minimum of the function. Alternatively, if the leading coefficient is less than 0, then those are parabolas that are going to open down. And in that situation, the vertex will provide a maximum value. The x value of the vertex tells us the location of the maximum in this case. And again, it's the function value itself, which is the y-coordinate of the vertex, which is going to be the max value. Okay. So when a is greater than 0, the function f has a minimum that occurs at x equals negative b over 2a. And that minimum value is the function value f evaluated at negative b over 2a. Similarly, if we have a less than 0, then that's going to produce a maximum for the function because it opens down. So the vertex is a max. The x-coordinate of the vertex, negative b over 2a, is where it occurs at. Yet the actual max value is that from the function. It's f of negative b over 2a. Let's take a look at example 4. They ask us to determine without graphing whether the function f has a min or max value. So that's going to be determined by the way that it opens. For this one, we see that a, the leading coefficient, is negative 3, which is less than 0. That means that it opens down. And because it's going to open down, that means that the vertex is a max. So this one's going to have a maximum value. Part B asks us to find the minimum or maximum value and where it occurs at. Again, this is going to be the x equals negative b over 2a is going to be the location of it. So it's going to be the opposite of b divided by twice a. Let's come back up here and take a look at our expression. The coefficient a is negative 3, b is positive 6, and I don't have to state it, but c is negative 13. The opposite of b is going to be the opposite of 6, divided by 2 times a, which is negative 3. This is going to be negative 6 divided by negative 6, which gives us positive 1. So it's going to occur at x equals to 1. And then the maximum value is going to be f of 1. So you now plug that x value into the function. This is going to be negative 3 times 1 squared plus 6 times 1 minus 13. that's equal to negative 3 plus 6 minus 13, which should be equal to negative 10. And so that's the max value. From this information, we can state the domain and the range. The domain of any quadratic function is always all real numbers. And we can determine the range from the information that we just found based upon the way that it opens and then the value of either the max or min. Remember, because this one opens downward, it's going to go all the way to negative infinity. And it's going to go up to the highest point on this parabola is going to be given by the y value of the function, its vertex, which is the same thing as its maximum value, which is negative 10. So domain all real numbers from negative infinity to positive infinity, and the range is going to be from negative infinity up to negative 10 when it opens down. That's the maximum value. The next thing we're going to look at is some applications of quadratic equations. There are many applied problems in the real world that results in a type of quadratic formula. Let's take a look at example 6. They say that when a football is kicked into the air from a starting height of 2 feet, the height of the football, f of x, is a function of the horizontal distance traveled by the ball x. It can be modeled by the following function: f of x equals negative 0.01 x squared plus 1.18 x plus 2. The first question says, what is the maximum height obtained by the ball, and how far does the ball travel before it makes its impact with the ground? Excuse me, what's the max height and where does it occur relative to the point of impact? Well, if we're looking for max height, again, this is a quadratic function. That's going to occur at the vertex. Notice that it does have a max because a is negative 0.01, which is less than 0. So we know that this one opens down. So it is indeed the case that the vertex will provide a max. Let's now find that vertex to determine the location. The x-coordinate of the vertex is negative b divided by 2a. Please make sure you have the vertex formula memorized. It's very important for the next test. A has a value of negative 0.01. B has a value of 1.18. And C has a value of 2. So it's the negative of B, that's negative 1.18, divided by 2 times A, which is negative 0.01. This is negative 1.18 divided by negative 0.02. If we work out that value, we should get 59. Keep in mind that this is a real-world problem, so these should have units with it. That's going to be 59 feet. Okay, so the ball reaches its maximum height at a distance of 59 feet from where it was kicked. To find the actual value of the max height, how high it goes, remember, we need to evaluate the function at that x value. So we need to find f of 59. This is going to be negative 0.01 times 59 squared plus 1.18 times 59 plus 2. And we should get about 36.81. 36.81 feet would be the max height. Now, keep in mind, and this is something that is very important. So whenever you're presented with questions like this, the question was a worded question of an applied problem. So we really should give a worded answer. So let me just kind of go ahead and write in sentence form what you should be putting down for this. We would say the ball reaches a max height of 36.81 feet after it has traveled and it was 59 feet horizontally. Let's take a look at part B. How far does the ball travel horizontally before it hit the ground? Well, the ball is going to hit the ground, means the height is going to be 0. So this ball hits the ground when its height equals to 0, which means that we need to set the function f of x equal to 0 and solve for x. So we want to know when is negative 0.01 x squared plus 1.18x plus 2 equal to 0. We can plug this into the quadratic formula, to the quadratic equation. And we should get the following solution. X equals negative b plus or minus the square root of b squared minus 4 times a times c, and I'm going to try and squeeze it in here. Just 2. All divided by 2 times a. So it's a little bit of calculator work. Let's go ahead and plug that in. If we plug these into our calculator or evaluate them, we should get 2 solutions because of the plus and the minus. One solution we get is x equals negative 1.67. The other solution will be x equals 119.67. Again, keeping in mind that this equation is only valid for positive values of x, which represent the distance traveled by the football after we kick it. The negative solution doesn't make any sense, and so the answer is going to be x equals 119.67. So again, I'm not going to write this one in complete sentence form, but you should yourself write it out as the ball will hit the ground after traveling 119.67 feet horizontally. With this information, we should be able to now go ahead and do a pretty accurate graph of the projectile, the path of the ball. Remember, it's kicked from an initial height of 2 feet. So this ball is going to start off at a height of 2 feet. It's going to initially start to travel up, 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 and we know that it reaches a maximum height of 36.81. So 36.81 is going to be the absolute highest this ball travels, and that happens after it travels 59 feet. So over here, once it's traveled 59 feet horizontally, it's going to attain the maximum. So that's when the ball is at its highest. It goes up until that point, and then it's going to slowly, after that point, it's going to start to go down, down, and down, and then it's going to hit the ground at x equals 119.67 feet. And so this is the graph that shows the projectile motion of our football. Let's take a look at one more. In example 7, it says you have 600 feet of fencing to enclose a rectangular plot that borders a river. So we have some fencing, and we're going to put it around a river so that we kind of have like a natural border here on this side. We're going to use x feet for the width of it. And let's suppose that whatever's left over, if you use x and x, that's 2x worth of fencing. What's left over would be 600 take away 2x, and that's how much we're going to have for the length of this thing. The question is, what dimensions should we make the fence? In other words, what's the length and the width that will provide us the largest enclosed area possible? So we're trying to maximize, in this case, the area of a rectangle. So let's first of all write out the formula for the area of a rectangle. It's length times width. The diagram is very helpful in this case. They've already diagrammed it for us, but the length is given by 600 minus 2x, and the width itself is given by x. So we see that our area function here, our a of x, area is dependent upon only the variable x. Let's rewrite this thing. Let's distribute the x in. This is 600x minus 2x squared. We notice the presence of the x squared term, so this is going to be a quadratic function. Let's rewrite it in standard form. We have our negative 2x squared plus 600x, like this. And notice that if you look at the type of quadratic we get, the leading coefficient, lowercase a, is negative 2, which is less than 0, which means that this function is going to be one that opens down, and so we will indeed get a maximum value. And that maximum is going to be given by the vertex. So now let's go ahead, let's find the vertex of this thing using the vertex formula. It's x equals negative b over 2a, like this. The value for b is 600. The value for a is negative 2. So we get negative 600 divided by negative 4, which is going to be 150. So the width that we would want to use here, the width that's going to provide the maximum is going to be 150 feet. We also need to give the length. Remember, the length was 600 minus 2x, which is 600 minus 2 times 150. That's going to end up being 600 minus 300, which itself will be 300. So those will be the dimensions that will give it to us. Now, they still ask the question of what is the maximum area. To find the actual value of the maximum, remember, we need to plug this into the function. So the max area is going to be found by the function value at the vertex. That's going to be a of 150. Let's take this and plug this back into our area function. It's going to be negative 2 times 150 squared plus 600 times 150. When we work this out, here's what we get. We get negative 2 times 150 squared plus 600 times 150, which is going to give us 45,000. Keep in mind that this is an area, and so it's going to have dimensions of feet squared. So if this is our real-world problem, we have now figured out the way to do it. The largest possible area is 45,000 square feet by using a rectangle with a width of 150 feet and length 300 feet.